61. Piecewise. So first thing we want to do is sketch it. So let's see. F of x equals, we got sine x between negative 2 pi and 0. And then we've got cosine x when I'm between 0 and x. So remember how we graph piecewise functions, or the easiest way, I think, to graph piecewise functions is plug in those domain restrictions, right? In this case, because I've got this sine wave, I might have to do a little more than just these. But at negative 2 pi, what's the value of sine? So I loop all the way back around, so I'm at 0, so the sine is 0, right? So negative 2 pi, and I'm going to go by half pi's here. Pi over 2, negative pi, 3 pi over 2, because that's generally what we do. Y'all remember graphing trig functions or not? Okay. At negative 3 pi over 2, what is sine? And I've got enough now that I can pick up this pattern, because I'm going to go until I get to 0, right? Is that right? Down, down, yes. This, there you go. Which is an open dot. So this piece of the graph looks like that. Are we all in agreement? And then the next piece of the graph, I'm going to start with 0. What's the cosine of 0? 1. Open or closed? Closed. And now let's move on half pi's again. So this is pi over 2, pi, what am I going to, 2 pi? 3 pi over 2, and 2 pi. What is the cosine of pi over 2? 0, right? And now I can pick this pattern up. Oh, yep, closed. So this piece looks like that. Everybody okay on the graph? At what points in the domain, so my domain for this entire function is going to be from negative 2 pi to 2 pi, right? You see that? Because that's where I've got graph defined. So every place that the graph is drawn, so from here to here, where do I have a limit that exists? Huh? So that's where it doesn't. So everything except 0, right? So I might say that the limit as x approaches, was it c of f of x exists on, and then from negative 2 pi to 0, but I don't want to include 0, and then from 0 to 2 pi. Actually, no, I cannot do. I can't include the endpoints because the limit doesn't exist on the endpoints. Do you agree? Why would the limit not exist on the endpoints? There you go. Definition of a limit says that the limit has to be the same from the left and the right. So for the endpoints, you only got it coming in from one side, so you don't have a limit there. So the limit's going to exist between negative 2 pi and 0, and then from 0 to 2 pi. Yeah. Okay, so 0 is not included because if I do the limit as x approaches 0 from the left, what do you get? 0. What's the limit as you approach 0 from the right? 1. In order for the limit to exist, those two values have to be the same. That's why. Which answers part C and D? Oh no, it doesn't answer them all. At what points does only the left-hand limit exist? Only the left-hand limit. Don't be shy, y'all. I agree with one of those. Only the left-hand limit, so no right-hand limit. Not where does the limit itself not exist, but just a left-hand limit. So yeah, 0 has a left-hand limit, but it also has a right-hand limit, right? But you are right about 2 pi because it only has a limit as it comes in from the left. It doesn't have a right-hand limit. Do you see that? I'm going to guess most of you put 0 and 2 pi. But 0 has a left-hand and a right-hand limit. They're just not the same. But 2 pi only has a left-hand limit. There's no graph over here coming in from the left. From the right. Does that make sense? So part C, at what point C does only the left-hand limit exist? 2 pi. Part B, at what point in the domain does it exist? Here. Sorry, this is B. This is C. I'm all over the place. What? This point right here is the only one that has just a left-hand limit. Okay, so this point, this green point, it only has graph on the left of it. It has no graph on the right. Right? Well, the left-hand limit only comes in from the left. So start to the left side of the point and then approach the point. So this is to the left of the point, right? So as I come in, it's a left-hand limit, but you move to the right to look at it. Is that where it's confusing? Okay. So start at the left side of the point, but go to the right towards it. Does that make sense? I feel like no. I feel like I'm confusing you a little more. You sure? Okay. Well, look at part D. What point only has a right-hand limit? So if you look at this graph, this one only has the graph on the right side. There's no graph on the left side. So there's no left-hand limit. There's only a right-hand limit. Limits stink, y'all. I'm sorry. Does that make sense? What else? 73 is C. 74 is B. 75 is D. And 76 is C. Did y'all get those right? Yes. 74. What is the value of the limit as x approaches 1 from the right of f of x? I guess you need, we haven't done a whole lot where we do it algebraically, have we? We should talk about this for a minute. Remember, I want to use substitution whenever I can, right? As I approach 1 from the right, so which piece of that graph is coming in from the right-hand side? The second one. Do you see that? This is from the right, so this is the one from the right, because if I think about x, the right-hand side is where x is getting bigger, right? So what happens if you plug 1 into that second equation? Does that make sense? You're just choosing, it's essentially you're choosing which equation fits, and then you're plugging into the one that fits. What else? Find the limit graphically. Use the squeeze theorem to confirm your answer. Approaches 0, x sine x. Okay, we'll graph it first. Y equals x sine x. I'm going to do a zoom 7. Ooh, I better come in some. Why did it do that? Let's go. Did I hit zoom trig? Okay. Let's come in. Oh, you know what? That's why. Always make sure you're in radians. I said graphically, it looks like the limit as I approach 0 is what? 0, right? So let's confirm it with the squeeze theorem. I know that the sine of x, the limit as I approach 0 of the sine of x, is going to lie between what and what all the time? Or actually, not the limit as I go to 0. Sorry, don't put the limit in there yet. I know that the values of sine of x lie between -1 and 1. Agreed or disagree? So now let's add this extra x in here. So negative x are equal to x sine x less than or equal to x. Meaning if I graph both of those, that function should lie between those two values. Well, they cross, but I can't see. There you go. Always between them. You see that? It's always between somewhere. I think that's so cool. That's like that other one we did. Okay, so since the graph itself is always between these two functions, then therefore I can say that the limit as x approaches 0 here has got to lie between the limit as x approaches 0 of the ends. Well, we know that both of those are what? 0. I can plug in, which means that if this value has to be between 0 and 0, it's got to be 0. So that means that the limit here would be 0. Yes. You haven't gotten to good squeeze theorem questions yet, but you will. I know. This is just kind of getting you used to it. But I think it's cool to graph them and watch it, how it falls between those. I know y'all are not impressed. I think it's cool. Thank you. Yes, Hope. Which one? 59. I'd be more than happy to. I like working these. 59. It says to draw the graph and then find the limits from the left and the right and determine if the limit exists. So I've got c equals 1, which means I'm doing the limit as x approaches c from the left and right. So as x approaches 1 from the left. 1. So here's my function. F of x equals 1 over x minus 1 when x is less than 1, and x cubed minus 2x plus 5 when x is greater than or equal equal to 1. So I'm going to find those endpoints again. Oh, I can't find the endpoint there, can I? Because if I plug it in, I get, ugh. So we know that what's happening at 1? A vertical asymptote. That's exactly right. And if you think back, do y'all remember those parent functions we learned in pre-cal? Remember the reciprocal function? The parent function of the reciprocal function looked like this. Remember that? No? Yes? Maybe? This one is the reciprocal, because this is 1 over x. This one is just shifted to the right 1 unit, right? So now, I'm thinking asymptote at 1. Did I just go out? I don't know why it keeps doing that. And I want less than 1, so I'm going to be on this side over here. So I kind of know what it's going to do. And I really probably, because I'm finding the limit as I go to 1, I'm not even going to need any points. I can just graph like this because I know what that parent function is. And then on the other side, I have this nasty cubic. If I plug in 1, I get 1 minus 2, which is negative 1 plus 5, which is 4. All right. 1, 2, 3, 4. Accordingly, we're going to wait on Hope to get back before we finish that problem, and we'll come back. So what'd you say, Cece? I didn't want one of y'all to go back and watch the thing at some point. The limit as x approaches 0 of, oh, this is a good one. As funky as that is, I still know that every sign still falls between -1 and 1, right? Agree? So now x squared, squared. So negative x squared. Y'all know I'm going to graph this because I love to watch how they fall between. So let's see if it really works. Sine, let's see, x squared sine of 1 over x squared. Y'all are not impressed by this, I know. Yes. No, I forgot what the thing was. X squared. X squared sine of 1 over. You tired of me? Then I'm going to go negative x squared. And I'm going to go. And I'm going to go. There's my x squared times. Still between them. It still bounds them. It's cool. Okay, so it looks like by the graph it should be 0, right? Even if I take off, let's take these off and look at it graphically. Still looks like it should be approaching 0. What's happening? It's doing some funky stuff in here. Maybe I can see a little better. Looks like it's doing that oscillating thing in there again, doesn't it? See what I'm talking about? Cool. You want me to zoom in some more? Okay. Thank you, Greg. What the heck? I gotta call Dean and tell him. Look at that. Oh, I didn't mean to hit that. I didn't mean to do that. I didn't mean to do that. That's not cool. Why are they doing it now? What did I do? Come on. Negative, let's go pi over 8. And pi over, no. Huh. It is super small. The calculator can't handle it. But see how the oscillations are trying to do? It's cool. I don't care what y'all say, it's cool. Okay. So it's 0, right? Because the limit as I go on the x squared and the negative x squared is 0. The limit as I go to 0. Limit as I go to 0. Limit as I go to 0 are all going to be. What else? Huh? I think some of this stuff you're going to know, and I'm going to tell you some kind of ways to kind of look at it. But all right, so as we look at these limits with infinity, I'm going to be looking at going to infinity or limits that approach infinity. But I want to be really careful because the number properties that I've used before don't always work with infinity because infinity is kind of conceptual, right? There's not really it's not like saying the limit as x approaches 2 and I can just plug in a 2 and then doing the limit as x approaches. In fact, let's do one we know. Of infinity of 1 over x is hard just to plug in an infinity, right? I have to kind of think about it. If I were to plug this in, right, because that's always what I want to do if I can. I want to try to plug in to evaluate. Well, if I do 1 over infinity, let's think about what that means. Because you know that this one should be what? You know what it should be here? 0, right? This is that reciprocal function that has the asymptotes at 0, x equals 0, y equals 0. So as I go to infinity, it should be approaching 0. Would that make sense to you if I told you 1 over infinity is 0? Why? Why does that make sense? That's exactly right. As this number on the bottom gets really, really, really big, the bigger the number on the bottom gets, the smaller the whole value really is, right? Think about it. A half compared to a 4, compared to an 8, compared to 100. This is getting smaller and smaller, right? You're getting less and less of the pizza if you get that much of a pizza. Of course, I think about food. But you're getting less and less. It's getting closer and closer to 0. So this, I could say, goes to 0. Does that make sense to you? No? Yeah? Okay. All right. And we also know that if I have a limit either infinity or to negative infinity and it equals some constant, then what do I have? An asymptote. That is by definition what an asymptote is, right? Horizontal asymptote, we talked about that I think in pre-cal. At least we did yesterday or day before yesterday in pre-cal here. But as you go to infinity, if you approach a constant, you're really what you have is a horizontal asymptote. Yeah. Notice I said or here because it could go either side. Remember we encountered some kind of crazy graphs that might have asymptotes on different sides. So let's do some algebraic Abby, you don't look too happy. Let's do some algebra. Me too. I had this bright idea that on Monday night I stayed up later because I normally go to bed really early, and I was like, maybe I'm getting like too much sleep and it's making me more tired. And so I went to stay up, and I was like, oh yeah, I felt really good Tuesday. So then I did the same thing on Tuesday night, and I was like, yeah, because yesterday I felt really good, and so then last night I did it again. Well, apparently there's a limit to how many times you do that because now I'm super tired. Okay, let's look at one algebraically. Let's say I have define f of x. I want you to find the limit as x approaches infinity, and then we're also going to find the limit as x approaches negative. I'll do the first one with you, and then I'll let you see what you get for the second one. So let's think about, I know I can't really plug it in, but let's think about maybe kind of plugging it in a little bit. So if I did, I would have infinity over the square root of infinity squared plus 1. Well, if you're squaring infinity and then you add 1 to it, you really haven't made much of a difference, right? You agree with that? I mean, you're talking about infinity plus. Remember, I have to kind of think about it conceptually. So really, I could say that's trivial. This is really infinity over the square root of infinity squared. Would you agree or disagree? Yeah? Well, I know that these two cancel. Well, now I'm at infinity over infinity. Can I call that 1? Maybe? We'll see. Let's see if that's actually 1. We'll graph it and see what happens. Well, because it's infinity. So if you have infinity and then you add 1 to infinity, what do you really have? It's really still infinity. I'll have to read y'all my hotel infinitum story or infinium story. It's long though, but we have an infinite number of rooms, but we have no vacancy. But up we have infinity plus 1 rooms. So how many rooms? It's a cool little. I'll read it to you. I didn't write it, but it's still. Okay. That's what I'm thinking it is. Now, if that is indeed 1, what should be happening at 1? An asymptote, because by definition, if I approach infinity and I get a constant, then that should be an asymptote. An asymptote. So let's graph it and see. What happens here? No. Square root of x squared. I didn't need that extra plus 1. Then 6. Oh. It does look like there's an asymptote at 1, so that is indeed correct, because graphically the limit as x approaches infinity. That's pretty cool, right? You try the other one. How about the limit as x approaches infinity? You can probably look at the graph and know what you should get, but see if you get it algebraically and it makes sense. Get it? You still working? If I plug in negative infinity instead of positive infinity, what really changes the sign. That's just the sign there. So here, because I'm squaring a negative, right, that becomes positive. I mean, what happens if you square infinity, really? You're still at infinity, yes? I mean, infinity times infinity is still infinity. So now I've got negative infinity. Actually, I shouldn't cancel squared out. I really should just set that backwards. I'm getting ahead of myself. Squaring a negative makes it positive. The one's irrelevant, and it is going to cancel with that radical again. So what I end up with is negative infinity over infinity, which looks like, and is that graphically what we get also? So you see how you have to be kind of conceptual about it as you look at those infinities and things? Okay. Everybody okay? Oh, I'm glad you asked. We're going to talk about that too. But when you have, this is, let's see, when this is a constant and you get infinity or negative infinity as what it equals, that's when you have a vertical asymptote. So vertical asymptotes are when you do the limit as x approaches a constant, either from the left or the right. If you get positive or negative infinity, that's a vertical asymptote. This is number 76. No, that's what I wrote down, but that's not true. That's a lie. What do you think the limit here is? One. It is. It's still one. How about if I do negative infinity? Why is it still one and not negative one? The absolute value is forcing positive, right? So if I graph this, I should see one and only one horizontal asymptote at y equals 1. Do you agree? Do you see how we can find? Remember in pre-cal we really focused on top heavy, bottom heavy, same, and we didn't really talk about other ways to find horizontal asymptotes. Well, this is another way to find a horizontal asymptote, is finding the limit as you go through. Y'all okay? Okay, I'm not going to go through all the properties of limits because all the properties that you had before are exactly the same as far as being able to split them up. Just because I'm going to infinity doesn't change the property. If I'm adding, I can split up the adding. If I'm multiplying, I can split up the multiplying. Let's do a sandwich theorem. It's the thing. It's the way it's formed. Does it stink? It's really strong the first day, but then it kind of not as strong. Hello, my old friend. Familiar, yes. What did we talk about this? What did we talk about this special one? The limit as x goes to what on this one? Did we do the limit as x goes to 0 on this one over and over and over again? And what did we find out it was? 1. But now my question is, how about if I go to infinity instead of to 1? What happens if I plug in? Let's try it, because I always want to try it if I can. That's a little, right? What's happening is That's it. I don't know. I don't know, right? Because sign's oscillating, yes? Changing. So really, I don't think I'm gonna be able to use that. But I can use what? The sandwich theorem. Because I do know that sine x is going to always fall between -1 and 1. So now, essentially what I'm going to do is divide everybody by x. So sine x over x should fall between that reciprocal function and the reflection of that. Woo, that stuff is strong right now. Okay. I'm going to cut it off. Agree or disagree? Thank you, Henry. Agree. I agree too. Now can you evaluate the limit as x approaches infinity? Yes, I hope you can anyway. And you should find how about on the left side? What's the limit as x approaches infinity of -1 over x? Well, we said if we plug that infinity in, right, we end up with -1 over infinity, which is really 0. It doesn't matter that it's negative because it's still getting really, 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 really small. How about the right side? 0. What does that tell me about this? It's 0. So then they don't always equal 0. It might be between two values, and you might just have to say that the limit lies between -1 and 0, or that the limit lies between -1 and 1. But if you get the same value, 1 and 1, or 2 and 2, then you know that the inside has to be 2. The same thing. You see what I'm saying? So if these are the same, then that means that this one has to be the same too. So the limit as x approaches infinity of sine x over x equals 0. Y'all good? Well, if you want to try, and then I'm gonna let you start trying it. No, you do whatever you think you need to do. We'll do it in behavior models. No, because at the end of the day, bless you, no matter what you're plugging in there and you're evaluating the sign at any particular value, it's still between -1. Sure, you can probably guess what this is going to be before you even work it. By definition, if I go to infinity and I get a constant value, that means there's a horizontal asymptote, right? So is there a horizontal asymptote at 0? No? You don't think so? But what's it oscillating towards? Right? Let me go out further on both sides. Well, we're going to infinity, so let me take it out. Let's take that x max out to, right now it's 2 pi. Let's take it out to 8 pi. Okay, so can you cross the horizontal asymptote? Yes, sometimes you can. It's just that instead of it approaching it this way, it's approaching it like, I know. What do you mean? Because now, instead of, remember your original amplitude definition of a horizontal asymptote or an asymptote in general? It's this invisible boundary that you can't cross as it approaches. Well, now we have a new definition. A new definition. I know, I'm sorry. It is bounding it, but it's that the function, the closer you, the further out you get, as you approach infinity, it's getting closer and closer to the boundary. So if you're getting closer and closer to a number value as you go to infinity, that's the horizontal asymptote. So it could squeeze in like it's doing it in strict line. So you get really right, but it's still not right, and it will cross it, but it's still approaching that. So yes, sometimes it can cross that. Say again. Yes. Well, not when x is 0, because x can't ever be 0 in this one, but it's hugging closer and closer to the y. You see it? It's approaching to where all the values will eventually be 0. It's a little more, does that make a little bit of sense though? So by definition now, I can say that this has a horizontal asymptote at y equals 0, even though looking at the graph, this does not look like a horizontal asymptote that we're used to seeing, right? But do you see how they're coming in towards this invisible line? Okay, so that is now our definition of horizontal asymptote. Anytime algebraically you can do this and you get a value, oops, it was 0, wasn't it? That is a horizontal asymptote at y equals 0. So now instead of just top heavy, bottom heavy, same, which we will still do, we're going to say, does it have any horizontal asymptotes? Well, what's the limit as the function, as x approaches infinity? What's the limit as x approaches negative infinity? And we will test for asymptotes that way. Does that make sense? All right, have y'all had enough for today?